Arumugalakshmi. Today we are going to discuss the problems in lesson 11 waves of class 11 physics. The first problem, the speed of a wave in a certain medium is 900 meter per second. If 3000 waves passes over a certain point of medium in 2 minutes, then compute its wavelength. So the given data is speed is given as 900 meter per second. We are supposed to find the wavelength. So first let us find the frequency using the formula. Frequency is equal to number of waves divided by time. Substituting the number of waves as 3000 and time as 2 into 60. Here we have converted 2 minutes into seconds. So only it is 2 into 60. Now dividing 3000 divided by 2 into 60, we get the answer as 25 second power minus 1. This is the frequency. Now we have to calculate the wavelength. We use the formula V is equal to n lambda. We reverse that formula to get the wavelength as lambda is equal to V by n. Now substituting the V value which is velocity and n value which is the frequency, we get lambda is equal to 900 divided by 25, which is equal to 36 meter. So the wavelength value is 36 meter. Now the second problem. Consider a mixture of 2 mole of helium and 4 mole of oxygen. Compute the speed of sound in this gas mixture at 300 Kelvin. So we have to calculate the speed of the sound and the temperature is given as 300 Kelvin. So first we are going to use the formula speed is equal to square root of gamma RT divided by molar mass. So we have to calculate the total molar mass of 2 mole of helium and 4 mole of oxygen. That is the first thing what we are going to do. Next we will be calculating the gamma value which is equal to Cp by Cv. So after calculating the total mass, we will be calculating the Cp value, Cv value. Finally, all those values we will substitute in the equation V is equal to square root of gamma RT divided by M. So first, for the mixture of helium and oxygen, the molar mix formula is N1M1 plus N2M2 divided by N1 plus N2, where N1 is the number of moles which is given as 2 for helium and M1 is the molecular mass which is 4 for helium. So substituting that value we get 2 into 4 plus N2 and M2, this is for oxygen. For oxygen, N2 is the number of moles which is 4 for oxygen, that is given in the data. M2 value, the molar mass of oxygen is 32. So substituting the value we get 2 into 4 plus 4 into 32 divided by 2 plus 4, which is equal to 136 divided by 6. So the total molecular mass of the mixture is equal to 22.6 into 10 power minus 3 kilogram per mole. Now we have found the total molecular mass. Next we have to calculate the Cp value and Cv value. We know that helium is a monoatomic. So the Cv value is equal to 3R divided by 2. Similarly, oxygen is a diatomic. So Cv2 value is equal to 5R divided by 2. So for the mixture, Cv value is given by N1Cv1 plus N2Cv2 divided by N1 plus N2. Now substituting the Cv1 value, Cv2 value, N1 and N2 in this equation, we get Cv value as 2 into 3R by 2 plus 4 into 5R by 2, the whole divided by 2 plus 4. Now cancelling the terms, we get the total Cv as 13R by 6. Now using the Mayer's relation, we know that Cp is equal to Cv plus R. So you can find the Cp value as 13R by 6 plus R, which is equal to 19R by 6. Now we have calculated Cp value, Cv value. Now we will substitute in the gamma equation. Gamma is equal to Cp by Cv. So substituting the value, we get 19R divided by 6 into 6 divided by 13R. So cancelling the terms, we get the value of gamma as 19 by 13. Now we have to include the Laplace correction also in the speed of the sound. So the value of velocity is equal to square root of gamma into RT divided by N. Substituting the values, we get square root of 19 by 13 into 8.31, which is the R value, into 300, which is the T value, the whole divided by the total molecular mass, which is 22.6 into 10 power minus 3. Simplifying, we get the velocity as 400.9 meter per second. Now the third problem. A ship in a sea sends sonar waves straight down into the seawater from the bottom of the ship. The signal reflects from the deep bottom bedrock and returns to the ship after 3.5 seconds. After the ship moves to 100 km, it sends another signal which returns back after 2 seconds. Calculate the depth of the sea in each case and also compute the difference in height between two cases. So the speed of the sonar waves in water is given as 1500 meter per second, and case 1, the time taken to reflect the sound from the bottom of the sea is equal to 3.5 seconds. Here the total time is 3.5 seconds. That is, sound is traveling from ship to the seabed. After that, from seabed it is reflected to the ship. So the total time is 2t. So 2t is equal to 3.5 seconds. So t will be equal to 3.5 divided by 2 seconds, which is equal to 1.75 seconds. Now we have to calculate the distance covered in forward and reflected backward. This distance we will have it as d1. So we are using the velocity formula. Velocity is equal to distance by time taken. Using this formula, if we reverse this formula, we get the formula for distance as distance is equal to velocity into time. Now substituting the velocity value and the time value 1500 into 1.75, we get the total distance travelled as 2625 meter. This is for case 1. Next, the ship is moving to a distance of 150 kilometer. Now the total time taken by the sound waves to be reflected is 2 seconds. Here also once again the sound is travelling totally 2t time. That is, from ship it is moving towards the seabed, that is 1 time. After that it is reflected from the bottom and it is reaching the ship. So the total time taken is 2t, which is equal to 2 seconds. So time is equal to 2 divided by 2, which is nothing but 1 second. So here the total time taken is 1 second. Now once again we find the distance covered by the waves, that is d2, using the formula velocity into time. Here also it is 1500 into time value is 1 second. So the total distance travelled is 1500 meter. So two cases we have found the two distance. Finally we have to find the difference between the height. So we have to subtract these two values, that is 2625 minus 1500. So the height difference is 1124 meter. Now fourth problem. A sound wave is transmitted into a tube as shown in the figure. The sound wave splits into two waves at a point. Now fourth problem. A sound wave is transmitted into a tube as shown in the figure. The sound wave splits into two waves at a point A, which recombine at point B. Let R be the radius of the semicircle, which is varied until the first minimum. Calculate the radius of the semicircle if the wavelength of the sound is 50 meter. So, we have to calculate the total distance travelled by the sound wave. So, the sound travelling in the curved path. curved path resembles a semicircle. So the total distance traveled is the total circumference divided by 2 because it is a semicircle. The total circumference of a circle is 2 pi r. Since it is a semicircle, 2 pi r divided by 2. So the curved path distance is pi r. So the distance length 1, L1 is equal to pi r. This is the first length. The second length is the sound is traveling in a straight line. So this we will consider as a diameter of the circle. So we know the relation that diameter is equal to 2 times radius. So the distance L2 is equal to 2r. Now we have to calculate the path difference. Path difference is given by L1 minus L2. So del P, which is the path difference, which is equal to pi r minus 2r. Here we can take r as common outside. So the equation of path difference becomes del P is equal to r into pi minus 2. This you have it as equation 1. We know that the difference in path length is equal to lambda by 2. So we have got two equations for path difference. So in these two equations, the LHS is equal. So we can equate the RHS. So equating the RHS, we get lambda by 2 is equal to r into pi minus 2. A small rearrangement, we have r is equal to lambda by 2 into pi minus 2. Now substituting the lambda value as 50, pi value as 3.141 and simplifying we get the radius value as 50 divided by 2.28 which is equal to 21.9 meter. This is the radius of the semicircle. The fifth problem. N tuning forks are arranged in an order of increasing frequency and any two successive tuning forks give n beats per second when sounded together. If the last fork gives double the frequency of the first, this is called as octave. Show that the frequency of the first tuning fork is f is equal to n minus 1 into n. We know that the total number of fork is equal to capital N. The frequency of the first tuning fork is small f. The frequency of the last tuning fork is 2f. This is like an arithmetic progression which is AP. So we use the formula for AP as AN is equal to A plus N minus 1 into D. Substituting the AN value as 2f, A value that is the frequency of the first one as f, plus n minus 1 into small n, where small n is the difference in frequency. Now taking the small f to the left hand side, we have 2f minus f is equal to n minus 1 into n. So 2f minus f is nothing but f. So f is equal to n minus 1 into n, which we have to prove. Hence proved. Sixth problem, let the source propagate a sound wave whose intensity at a point initially be I. Suppose we consider a case where the amplitude of the sound wave is doubled and the frequency is reduced to 1/4. Now you have to calculate the new intensity of sound at the same point. So intensity of the sound wave, old wave is given as I1. The amplitude of the new sound wave A2 is given as twice A1. The frequency of the sound wave only we have to find. So we know the relation I1 is proportional to F1 square A1 square. Similarly, I2 is proportional to F2 square A2 square. Dividing these two equations, we have I1 divided by I2 is equal to F1 square into A1 square divided by F2 square into A2 square. We know that the second frequency is reduced 1 by 8 times. So we have F2 is equal to 1 by 8 F1. Here it is F2 squared. So F2 square is equal to 1 by 16 F1 square. Similarly, the amplitude A2 is equal to 2A1. Here it is A2 square. So it will be 4A1 square. So substituting these two values, F1 square and A1 square will get cancelled. So after simplifying, you get 16 by 4, which is equal to 4. So the second intensity I2 is equal to 1 by 4 I1. Seventh problem. Consider two organ pipes of same length in which one organ pipe is closed and another organ pipe is open. If the fundamental frequency of closed pipe is 250 Hz, calculate the fundamental frequency of open pipe. We know the fundamental frequency of closed organ pipe. The formula as Fc is equal to V by 4L, which is equal to 250 Hz, which is the given data. We have to find the fundamental frequency of open organ pipe, which is F0. The formula is V by 2L. Now what we are going to do is we are going to divide the fundamental frequency of closed pipe divided by fundamental frequency of open pipe. So Fc divided by Fo is equal to V divided by 4L, the whole divided by V divided by 2L. So the denominator we are taking it to the numerator by reversing. So we get the value as V divided by 4L into 2L by V. Now cancelling the velocity and L, which is same, we get the answer as 1 by 2. That is Fc by F0 is equal to 1 by 2. So cross multiplying, we get F0 is equal to 2 times Fc. That is frequency of open pipe is equal to 2 times the frequency of closed pipe. Now substituting the frequency of closed pipe as 250. So 2 into 250, that is 500 Hz is the frequency of open pipe. The eighth problem. A police in a siren car moving with the velocity 20 meters per second chases a thief who is moving in a car with the velocity V0 meter per second. The police car sounds at frequency 300 Hz and both of them move towards a stationary siren of frequency 400 Hz. Calculate the speed in which the thief is moving. So we know that the velocity of the sound V is equal to 330 meter per second. The velocity of the car, which is the source, is given as 20 meter per second. The frequency of the car F1 is 300 Hz. The frequency of the stationary siren, we assume it as F2, is equal to 400 Hz. The speed of the thief, which is V0, that only we have to find. We know the formula, the Doppler effect formula velocity as V1 is equal to F1 into V minus V0, the whole divided by V minus Vs. Similarly, V2 is equal to F2 into V plus V0, the whole divided by V. Since both are moving towards a stationary siren, we have V1 is equal to V2. So, equating the above two equations, we have 300 into 300 minus V0, the whole divided by 330 is equal to 400 into 330 plus V0, the whole divided by 330. Now simplifying, we get 330 minus V0 is equal to 4 into 330 divided by 3 into 330 plus V0, the whole divided by 330. So 330 minus V0 is equal to 1240 divided by 990 into 330 plus V0, which is equal to 1.2525 into 330 plus V0. Now bringing V0 to this side, we have 330 minus V0 is equal to 413.325 plus 1.2525 V0. Now further simplifying, we get 2.2525 V0 is equal to minus 83.325. So V naught is equal to minus 83.325 the whole divided by 2.2525, which is nothing but 36.99. So the velocity of the thief is 36.99 meter per